In this session, we're going to solve quadratic inequalities. A quadratic inequality is an inequality that has a quadratic expression. Probably had that figured out already. We're just going to dive right in. We're going to use a graph to solve the inequality x squared minus x minus 6 is greater than 0. And here we have a graph of a parabola, quadratic, y equals x squared minus x minus 6. So here we're looking at the expression x squared minus x minus 6. And we want to know where that is greater than 0. Since we have here a relationship, or a function, y equals x squared minus x minus 6, this is the same thing as finding out where y is greater than 0. I don't want you to get hung up on that, though. What I want you to think about is that the y values are the output values, and below the x-axis all the y values are negative. Above the x-axis all the y values are positive, and on the x-axis the y value is 0. In other words, any part of the graph that is above the x-axis has positive outputs, and therefore y is positive. Any part of the graph below the x-axis has negative outputs, and so those are where y is negative. I see here that there are two x-intercepts for this parabola, and one of them is at negative 2, 0, and the other one is at 3, 0. So these are cutoff values that distinguish positive from negative function values. Here in our first example, we're solving the inequality where the expression is greater than 0. That means positive. So we're looking for where this parabola is above the x-axis. And the answer, because the expression is x squared minus x minus 6, is going to be in terms of x. And so if I can kind of bring our color coding to the x-axis, the parts where the function is positive, has y values that are positive, correspond to particular inputs on the x-axis. Likewise, where the function is negative, those outputs correspond to particular inputs on the x-axis. So I can see here that since all of the output values for x being less than negative 2 are positive, likewise all of the output values for x being greater than 3 are positive. Therefore, this original inequality, x squared minus x minus 6, is greater than 0 when x is either in the interval from negative infinity to negative 2, or the interval from 3 to infinity, and that's the solution to the inequality. Next, we have the same expression, but a different inequality. We're going to use that same graph to solve the inequality x squared minus x minus 6 is less than or equal to 0. Less than or equal to 0 has two parts. One of them is less than, the other is equal to. In other words, we are now going to include the points that are on the x-axis, and because we want values that are less than or equal to 0, we're going to include all of the values that are below the x-axis as well. Those function values correspond to input values that are between negative 2 and 3 inclusive. And so the solution to this inequality from the graph is negative 2 to 3 with square brackets at both negative 2 and 3. It seems that if we know what the x-intercepts are and we know how the graph plays out, then it's fairly straightforward to find out where a function is positive and where a function is negative. And we're going to see that throughout this session. Now, before we go on to our next example, let's look at this parabola that we have. It's a characteristic of a quadratic expression that the output values are continuous. That is to say, the graph doesn't switch from positive to negative without going through 0. It doesn't all of a sudden jump and change signs. So it's actually going to be sufficient for us to use intervals that are defined by zeros and then pick test points in the intervals. And the nature of the outputs, the positive or negative nature, is going to be consistent throughout that interval. And we're going to use that fact for this inequality, but first we're going to talk a little bit. We're to solve the inequality p squared plus 5p plus 4 is less than 0, and to give our answer in interval notation. I want to highlight a distinction between solving a quadratic equation and a quadratic inequality. If this were an equation, then what I could do is factor the expression, so I'd have p plus 4 times p plus 1 is equal to 0, and then I would set each factor equal to 0, solve the resulting equation. I can't do that with an inequality. I can factor it, and that'll help me to know what the zeros are. That'll help me to figure out the intervals. But I'm going to write down that p plus 4 times p plus 1 is less than 0. I do not get to split this up into two inequalities because it's important how these factors interact with each other. You'll see what I mean, hopefully, in just a minute. What I'm going to do is a basic three-point strategy. First, I'm going to find the zeros. Then, I'm going to pick test points that are in intervals defined by the zeros. And then finally, I'm going to write down intervals that indicate the solution. But whatever you do, do not split an inequality that has factors into separate inequalities. First, we're going to find the zeros. The zeros are negative 4 and negative 1. And we're going to consider this to be like a p-axis. Negative 4 and negative 1 divide the p-axis into three regions. Intervals, if you will. There's one to the left of negative 4, between negative 4 and negative 1, and to the right of negative 1. I'm going to pick test points that are in these intervals. A test point to the left of negative 4 is, I don't know, negative 5, any number to the left. Between negative 4 and negative 1, I use negative 2. And to the right of negative 1, I'm going to use 0. So, we have found zeros, we have picked test points. Now we're going to use the test points. For any particular input value in these intervals, I don't need to know the exact answer of the output. What I need to know is if it's positive or negative, because we're trying to solve an inequality that's being compared to 0. So for each one, I'm going to look at the individual factors of p plus 4 times p plus 1. We're going to start with negative 5. If p is negative 5, then p plus 4 is a negative factor, and p plus 1 is a negative factor. And I know that negative times negative is positive. That's going to indicate the character of all of the outputs to the left of negative 4 because of that continuity. For a p-value of negative 2, p plus 4 is a positive factor, p plus 1 is a negative factor, and positive times negative is, of course, negative. And so all the values, the input values from negative 4 to negative 1 will correspond to negative output values. Finally, if we use 0 as an input, then p plus 4 is a positive factor, p plus 1 is also a positive factor. Resulting expression is going to be positive, and so all the numbers to the right of negative 1 will give positive outputs. Now our original inequality asked us to find where p squared plus 5p plus 4 was less than 0. That corresponds to negative outputs. So our inequality's solution is going to be from negative 4 to negative 1, because that's the interval over which the outputs are negative, with parentheses because it was a strict inequality. Next, we have an inequality. 6t is less than or equal to t squared plus 25. It's a lot easier to compare things to 0 than it is to compare them to 6t. Therefore, I'm going to subtract 6t from both sides and end up with 0 is less than or equal to t squared minus 6t plus 25. Notice I put that expression in descending order. And here we have 0 to the left of the expression. 0 is less than or equal to. That can be confusing. So I'm going to reverse the inequality, or just like switch the inequality around. I'm going to put t squared minus 6t plus 25 on the left-hand side, and the 0 on the right-hand side, and then we're going to note the nature of the inequality. 0 is less than or equal to the quadratic, which means the quadratic is greater than or equal to 0, right? When we switch everything around, everything flips. Or another way to think of it is, if the inequality symbol was pointing at 0 and opening up to the quadratic, it should still point to 0 and open up to the quadratic. Now, generally speaking, we said we're going to find zeros and pick test points. Let's try to find a 0. I'm going to use the quadratic formula. T is equal to 6 plus or minus the square root of 36 minus 100 over 2. I mean, all over 2. I can see that the discriminant, 36 minus 100, is negative, which means the solutions would be complex, and so the quadratic expression is never equal to 0 on the real numbers. What we can conclude from that is the expression t squared minus 6t plus 25 is either always positive or it's always negative. It shouldn't be too hard to figure out which one it is. We can pick any test point. And so I'm going to pick a test point of 0. The expression t squared minus 6t plus 25, if t is equal to 0, is positive. It's 25. Therefore, the expression is always positive, and so it's always the case that t squared minus 6t plus 25 is greater than or equal to 0. Our answer in interval notation, negative infinity to infinity. We're going to explore just a hair now. Suppose we had t squared minus 6t plus 25 was less than 0. The same analysis with the complex zeros and the output value being positive for any output value indicates it'll never be negative. So this inequality would have no solution. Next we have the inequality x squared minus 4x is greater than or equal to negative 1. We're to solve it and give the answer in interval notation yet again. So I'm going to do the same thing we did before. We're going to get 0 on one side because it's a lot easier to compare to 0. So we have x squared minus 4x plus 1 is greater than or equal to 0. General roadmap, find zeros and then pick test points and write down intervals. Find zeros. This is not factorable, and so we could use the quadratic formula. However, I see that the leading coefficient, the one on x squared, is 1, and I see that the linear coefficient, negative 4, is even. To me, this makes a good candidate for solving by completing the square. And we're going to see that this is actually going to be not so bad. To find the zeros, I actually want to consider solving the equation x squared minus 4x plus 1 is equal to 0. And to solve that equation by completing the square, I'm going to write down that x squared minus 4x is equal to negative 1, leaving a space to complete the square. I know that to complete the square with a 4 on my x, we're going to cut that in half and square it, we get 4, so add that to both sides. The left-hand side factors into x minus 2, the quantity squared. The right-hand side simplifies to 3. And so x minus 2 is equal to plus or minus the square root of 3. And so x is equal to 2 plus or minus the square root of 3. That seems icky. Well, if we picture a number line, actually we don't have to picture it, we can draw it, and come up with approximations for 2 plus the square root of 3 and 2 minus the square root of 3. Let me get some calculator values for those. I get approximately 3.73 and then 0.27 respectively. So I'm going to mark on the x-axis 0.27, and then this may not exactly be to scale, but we get the idea, 3.73. Those are the intervals endpoints. So what I need to do is pick test points that are to the left of 0.27-ish in between 0.27-ish and 3.73-ish, and to the right of 3.73-ish. I'm thinking that good test points are going to be 0, 2, and 5. 0 is to the left of 2 minus the square root of 3. 2 is in between the two numbers. And 5 is to the right of 2 plus the square root of 3. What I need to know is the positive or negative nature of x squared minus 4x plus 1. This isn't quite as easy as if we had factors, but it's still not too terribly bad. If x is 0, the expression is 1, and so I'm just going to write positive because that's what I really care about. If x is 2, then we're looking at 4 minus 8 plus 1, which I can see is going to be negative, right? Less than 0. And if x is 5, we have 25 minus 20 plus 1, which I can see is positive. Therefore, all the values to the left of 2 minus the square root of 3 are going to give me positive outputs. Likewise, all the values to the right of 2 plus the square root of 3, and in between, all the values are going to be negative. Looking back at the original inequality, well, not the original one, the one where we had it isolated with 0 on one side, indicates that we are looking for values that are positive or 0, right? Greater than or equal to 0. So the way we're going to write this is we're going to say negative infinity to 2 minus the square root of 3 with a square bracket at that endpoint, union with another square bracket, 2 plus the square root of 3, comma, infinity. These are the input values that will give us a positive expression, or 0. Now we have something where this kind of gives this process some meaning. We're asked to find the domain of f of x is equal to the square root of x squared minus 2x minus 15. So here I am minding my own business, just trying to find the domain of a function, and because it's in a square root, I now all of a sudden have to consider where x squared minus 2x minus 15 is greater than or equal to 0, and just walking down the street, bam, I have to solve a quadratic inequality. I'm going to do so by factoring the expression on the left-hand side because this one is factorable. X minus 5 times x plus 3 is greater than or equal to 0. The zeros are easily obtained. Zeros are negative 3 and 5. Now I have found zeros. I need to pick test points, and then I'm going to write intervals. Or an interval, I guess we'll see. I would say that good test points would be, to the left of negative 3. How about negative 5? And then in between negative 3 and 5, let's go with 0. To the right of 5, 10. All I need is numbers that aren't those ones, negative 3 or 5. So if x is negative 5, the expression x minus 5 times x plus 3 is going to be a negative factor times a negative factor, and so is positive. If x is 0, we have a negative factor times a positive factor. And if x is 10, we have a positive factor times a positive factor. So the outputs are positive, and then negative, and then positive, as we would probably expect. Does it always work out this way? I don't know. It's probably a good idea to check every time. No, if we had a leading coefficient that was negative, then it would be opposite. But we already saw one where the graph was fully above the x-axis. It's best to just check your intervals. It's just safest. And like I said, we're setting up for future stuff. In any case now, since the inequality is greater than or equal to 0, right, the expression is greater than or equal to 0, we can write this down as negative infinity to negative 3 with a square bracket to include the end, and then union, square bracket, 5 to infinity, and this gives the domain of this function.